Welcome to qnawire.
Hi everyone, so what we have is a ballast tank in a submarine that has a total volume equal to 700 cubic meters. Initially this is filled up with a combination of air and water, where the air is taking up 100 cubic meters and the water takes up 600 cubic meters. We know that the air is at 1500 kPa and 15 degrees C, and air is actually pumped in at again 1500 kPa but at a higher temperature of 20 degrees C. We know that the water is leaving at a temperature of 15 degrees Celsius, and we're also given that the pressure and the temperature in the water, or temperature in the tank, are constant. So what we're asked to solve for is the final mass of air in this tank and the total heat transfer that occurs. The first thing we're going to do is write down our assumptions. So we're going to assume that air is an ideal gas, and that means that this air is going to have variable heat capacities. And we're also going to assume that the work is going to be equal to 0. So next we're going to go ahead and write down the properties of our gas. So we know we're dealing with air, so our gas constant is going to be 0.287 kilojoules per kilogram Kelvin. We can also look at the specific heats of air, so we can see that Cp will be equal to 1.005 kilojoules per kilogram Kelvin. We also have a Cv that's equal to 0.718 kilojoules per kilogram Kelvin. And lastly, we also can look at the specific volume of water, which is called that VW, and that's going to be equal to 0.001 cubic meters per kilogram. Now what we can do is solve for the initial mass of air just by manipulating the ideal gas law. We can say that M1 is equal to PV1 all over RT1, and actually P1V1 over RT1, and this gives us an initial mass equal to 1,814 kilograms. We can go ahead and solve for the initial mass of water by using the specific volume of water that we looked up. So this will give us a total volume of water in the initial, a total mass of water in the initial condition equal to 600,000 kilograms. Then we can also again use the ideal gas law to solve for the final mass of air in the tank by saying that M2 is equal to P2V2 over RT2, and this gives us a mass equal to 12,697 kilograms. And that is one part of our final answer. Next, what we're going to do is we're also asked to solve for the total heat transfer going through the system. And what we can do is say that the energy coming in minus the energy leaving is equal to the total change in energy of the system. And we can write this by saying that we have heat that's coming in plus enthalpy that is also coming in minus enthalpy that is leaving the system, which is going to be equal to the change in energy of the system itself. So that's going to be M2U2 minus M1U1. So we can actually go ahead and isolate the heat, Qin, and say that Qin is equal to M2U2 minus M1U1 plus MEHE minus MIHI. Now we can use the definition of Cp and Cv and relate them to internal energy and enthalpy, and go ahead and put the enthalpies and energies in terms of temperatures and our specific heats. So we can say that Qin is again equal to M2 CVT minus the quantity, the mass of air at 1, CVT, plus the mass of water, UW, plus MWHW, minus M2 minus M1 CPT. Now remember, the temperature is held constant throughout this process, so there's no designation between T1 and T2, it is just temperature. And by looking up in the table, we can see that the specific energy of water is going to be approximately equal to the specific enthalpy of water, which is equal to 62.98 kilojoules per kilogram. And by plugging all of these quantities in, we'll see that we get a final Qin equal to approximately 900,000 kilojoules. And that's our final answer. And that's going to be negative 900,000 kilojoules because the heat is actually leaving the system.